welcome back to 7th grade science. So far we've talked about rocks and minerals, and now we're going to talk about fossils, which we've covered a little bit as we've talked about how different rocks form. Now we're going to talk about it in a little bit, but it is important to remember that you are more likely to find rocks in sedimentary rocks. And remember, that's a less aggressive rock formation process than, say, metamorphic or igneous. Because igneous rocks are formed how? Right, through molten rock. So you take a rock, put it in magma or lava, it melts, new rock forms once it cools. And metamorphic rocks are formed through heat and pressure, so they can be damaging for items that are going to be fossils. But really, before we can talk about fossils, we have to talk about what fossils are. Fossils are preserved remains or traces of organisms that have lived in the past. The most commonly preserved parts are the hard parts, so your bones, teeth, which are a form of bone, exoskeletons, anything like that, shells. The harder the part, the more likely it is to survive the fossilization process. The softer the part, the less likely it's going to become a fossil, and the reason being it's a lot more likely to be destroyed during the fossilization process than a hard part. Now, that doesn't mean that hard parts aren't always destroyed either, but we'll cover that in a couple minutes. The hard parts, the bones, the teeth, the parts of the organism that is hard and becomes a fossil are known as body fossils. You can think of that like the human body or a T-Rex body or a clam body. Their body is inside the shell in reference to the clams, but the clam shell is hard and it's likely going to survive. Same for the bones of a T-Rex or the bones of a person, they're the harder part, so out of everything that makes us us, they're more likely to survive than, say, skin or hair or any other soft tissues. Just like you have body fossils, which are the hard parts, you can also have trace fossils. Trace fossils are preserved traces. So if you've ever gone out in a field and found a fossil rock where it's got seashell fossils or it's got leaves or different things like that, those are more likely to be trace fossils. When you're finding the shell fossil, are you finding an actual component of the shell or are you finding the trace of a shell? Because if it's the component of a shell, that's your body fossil, but more commonly it's the trace of the shell, the imprint that's left behind of the shell. Those are your trace fossils. Now these can include footprints. So if I am outside walking and then my footprints become fossilized, or a T-Rex footprint. They can be burrows, so if something digs underground and you can get a fossil of their tracks, whether it's like moles or woodchucks or something that lives underground that burrow. You can even have fossilized waste. Waste, this time, actually means dinosaur poop. So you could have fossils of dinosaur poop, which you'll see in our slides tomorrow. I got a picture of it. Any of these things are traces of the animal that get fossilized, so that's why they're trace fossils. They're not the animal itself. They're not necessarily the full imprint of the fossil or of the organism. They are just traces of that organism. Now that we know what fossils are, let's talk about the process of fossilization, which by definition is just the process of an organism becoming a fossil, whether that's a body fossil or a trace fossil. Specifically, it's the process in which living things become fossilized. Now, I touched on it in the beginning, but again, I want to reiterate that most fossils are formed in sedimentary rock. An organism dies, it gets buried in sediment layers. The sediment layers continue to build up and up and up, and eventually it turns to a sedimentary rock. Remember, you have your sediments that build, then they undergo cementation and compaction, and then you have a rock. Just this time, instead of it being a flat, even surface or just a flat layer, you've got something in there that's getting surrounded and squished down in, so it's getting trapped in that layer. Eventually, the remnants of the organism can turn into rock themselves. So the actual bones can be broken down and turn to rock. Well, they get broken down, then turned into minerals, then turned into rock. This is called permineralization. And this references when those organism parts turn to rock. They don't always, though. So what do I mean by they don't always? Well, we have different examples of fossils that are the preserved remains. So we have dinosaur bones, right? Are they necessarily the rock version of the bone, or are they the bone? Well, both, but under complete preservation, they're the bone. When an organism undergoes complete preservation, the organism is left relatively unchanged. Now, when this happens, we may be able to actually study the organism's DNA. And it's more common in things like ice, where we have mammoths or different organisms that got frozen in glaciers and different things and then they thaw out. But you can also have it with things like tree sap. So especially with insects, insects could get trapped in tree sap, which over time turns to amber. Inside that amber, the insect is relatively unchanged from hundreds of thousands or however long years ago that existed. So the organism itself and its DNA is pretty much the same now as it was then. Another spot that can help or show the complete preservation of an organism is tar pits. So as far as I'm aware, at least around here, we don't have tar pits just laying out where we're walking one day and then we get sucked down in. Back in the day, in different parts of the world, there were tar pits. And what would happen is the organism would fall into the tar pit, whether it's a plant, like if a tree limb falls into it, or if it's a dinosaur that gets caught in it. Then what happens, the animal itself, or the organism, because it could be a plant, gets trapped in the tar solidifies, completely preserves. Well, we've covered permanentization and we've covered complete preservation. Now let's talk about mold. And this isn't the kind of mold that you sometimes get on bread if you leave your bread out too long. This mold is more of an art-related thing where you can make molds. And it's an imprint that's left in the rock. Specifically for fossils, it's an imprint of an organism that's left behind in rock. In this instance, the organism completely breaks down. So this is like the shell imprints that I was talking about before with the trace fossils. You have your shell that gets put into rock, and over time that shell is completely broken down. That space ends up filling with other rock that molds itself into the shape that the organism once was. That new rock formation that looks like what was left behind in the mold is called a cast. And it's not the cast that you could have on your hand if you broke it. A cast is a fossil that forms within the mold. So it's those rocks taking on the shape of whatever organism left behind the imprint. Just like the other ones we talked about, this is typically found in sedimentary rocks. Think about it. Sediments form layers and build on one another and then form sedimentary rock. So if you've got an empty space that has a particular shape of, say, a seashell, and the sediments fill that layer, they're going to get compressed down into that shape, right? It's kind of like if we took cookie cutters and cut into cookie dough, we would be left with the particular shape of the cookie cutter. So it's a similar idea to that. Or it's like a mold that you use when you are making different candies. You melt the candy, put it in that shape, pop it out when it's done, and you have that shape in candy. Instead of candy, we're talking about rocks, but same idea. Now when I said rocks can fill a mold, can't minerals also fill a mold? Yes, they can. And remember, minerals can become rocks, or minerals do become rocks. Another type of fossilization that can occur is compression. Now, compression is a little bit different than molds and casts, because you could argue that a mold is filled with rocks, which then undergo compression, which leaves you the cast. But compression in this sense is where you're left with a dark stain. This dark stain is left in the shape of the organism on a rock. The remains of the organism are put under great pressure in between the layers of the rock, and then all that's left is not actually the remains of the organism, but just a dark imprint of it. So we've covered these different types of fossilization, but does it happen often? No. To be honest, fossils really rarely ever form. And the reason they rarely form has a lot to do with environments and whether or not those organisms or their remains can hold up long enough to make it into a fossil. Many remains are consumed or broken down by living or non-living things, whether it's like bacteria, wolves eating the dead dinosaur, anything along those lines, or if it's weather. So an earthquake or volcanic eruption or anything along those lines all have an impact on whether the tissue of the organism survives. Because remember, without the tissues either becoming rock or forming molds and casts or being compressed or leaving traces, you can't have a fossil form. The less hard parts an organism has, the least likely it is to become a fossil. So that's why it's super rare to find fossils of jellyfish or bacteria, different things that only have soft tissue. Or let's say my hair, if I just put this down on the ground, the likelihood that that would turn into a fossil is slim to none. I mean, it could blow away, exposure to different environmental factors. As far as I know, there's nothing animal-wise that really eats hair, but hey, in theory something could, and if it's eaten by something else, can it stay in one place to make a fossil? No. Just like with a lower amount of hard parts, the less likely something is to be a fossil, the more hard parts something has, the more likely it is to become fossilized. But that doesn't guarantee that it is going to become a fossil. Generally speaking, it is very unlikely for anything to become a fossil. Some things are just a lot more unlikely than others. So, who cares about fossils? What can we learn from fossils? We can actually learn a lot of different things from fossils. For example, we could be on top of a mountain, like we are right now in this video. And on top of this mountain, we are scientists looking for fossils. And look, we found this fossil up here on top of the mountain, 20,000 feet in the air. But this fossil looks like a seashell. How did a seashell get on top of the mountain? Well, one, if this is an index fossil, which we'll cover in a minute, we would get an idea of how old it is. And two, seashells are generally found on the sea floor, not on top of the mountain, right? Well, that tells us about different geological processes that occur. So essentially what had to happen was, at one point, the rocks that we're currently exploring on top of the mountain were actually rocks found at the sea floor. And over time that changed. One thing, or one way that it can change, is something called plate tectonics. Essentially, there are different plates on the Earth and they're moving. Sometimes they collide, and when they collide, you've got like slips. So one goes up, the other goes down. Oh look, we have a mountain now. We're not going to spend a lot of time on plate tectonics yet, because in a little bit here, after we're done with fossils, we're going to start talking about plate tectonics and continental drift. But for right now, it's just important to note that plate tectonics is one way you can have fossils or rocks from the seafloor end up in mountains. Now, let's say we had a massive earthquake tomorrow, or when you're watching this video. And what are the chances that we're suddenly going to have a massive new mountain form outside of the Atlantic Ocean? Probably slim, right? So this is a relatively slow process that occurs over many, many years. Basically, the takeaway I want you to take from that part is just that even though we have seashells at the top of a mountain where they shouldn't really be, it just shows how the Earth changes over time. And that's one thing that fossils tell us, is how environments change. Really, fossils are one of the best clues we have at what has happened over time to the Earth itself. Now, these clues they give us, I've kind of alluded to, and they include different geological events like different earthquakes or volcanic eruptions or different things that have happened throughout history, as well as different climates and the way that they were over time at different points in our history. So just like we talked about, the fossils on top of a mountain that really shouldn't be there in this day and age, in the sense of seashells don't form on mountains, that tells us that the Earth has changed, and it tells us how the shape has changed. What was once at the bottom of the seafloor is now way above the seafloor on top of a mountain. But they can also tell us how climate has changed in those areas. And a good example of this is finding plants in Antarctica, which last I checked was pretty cold, right? But at one point it was warm enough to support plant life. And so there were different plants that grew there. Those plants formed fossils, and now we can see, wait a second, it wasn't always that cold. Or at least, necessarily, I'm not talking about one of the poles at the highest point, but different areas show how over time the climate of different areas have changed. You could see where something that is a desert now hasn't always been a desert. And some of that's through fossils. These can really show the differences in climate, differences in environment that have changed significantly over time. Now, before I said I was going to reference index fossils. Index fossils are fossils of organisms that lived over a relatively wide area for a relatively short period of time. Now, as far as science is concerned, a relatively short period of time could be somewhere as long as 100 million years, or more, or less. In the grand scheme of the entire time that Earth has been around, that's a very small portion. It might seem like a lot to us, especially because to us, 10 years is a big difference, let alone 100 million. But as far as rocks are concerned, it's like 5 seconds. It's not really a big deal for rocks. These index fossils allow scientists to approximate the age of the rocks they're in. If you can get specific species, that can help narrow down the time frame even more, especially if you know that this certain species A of this organism only existed from the years 2000 to 2500, you would have a better approximation of the age of the rocks. Trilobites are good examples of index fossils. They're used relatively frequently as an index fossil. These are widespread, and they're approximately 500 to 600 million years old. Now, the reason that you want an index fossil to be widespread is because you know that it was a very common organism for that time period. If you had a very specific fossil type that was only found in, let's say, New Berlin, then that wouldn't necessarily be able to describe or approximate the ages of rocks in different areas, because that species is only found in one tiny little part of the world, not a large amount of parts of the world. Trilobites were found all over, and like I said, the range was about 100 million years of the time frame that they were found in. So it's a good index because we could say, okay, the rock found here in New Berlin where trilobite fossils were found is approximately the same age as the rock found in Egypt with trilobite fossils, because they're approximately the same time frame or the same age range. All right, folks, that is everything I have for you today. So as always, if you have any questions, please don't hesitate to reach out. Bye.